you ever noticed how a familiar object becomes unsettling the moment it refuses to behave the way physics says it should? That's what happened when new images of the interstellar visitor 3IATLAS reached research teams earlier this month. The data didn't reveal chaos or debris trails, just a stable, persistent glow and pulse patterns that didn't match any known class of comet or asteroid. Within hours, the findings pushed the United Nations to assemble a rapid response scientific mission, a decision usually reserved for far clearer threats. As we explore what triggered that urgency and why experts are suddenly divided, a quick like and subscribe helps the channel reach more science-minded listeners. Let's examine what the images really showed and why no one expected the consequences that followed. The United Nations initiated a planetary defense exercise focused on the object known as 3IATLAS after new images showed changes that scientists could no longer treat as routine. Earlier observations had already revealed odd behavior, but the most recent data shifted the situation from curiosity to concern. The tail now appears to stretch close to 5 million kilometers, and it is not only long, but sharply defined. Professor Avi Loeb then reported what he called the 12th anomaly in the behavior of this object. The first 11 anomalies already pointed to activity that did not follow standard expectations for comets or for interstellar visitors. Each irregularity on its own could be dismissed as noise in the data or a temporary effect, but the repeated appearance of these anomalies made it harder to view 3IATLAS as just another strange comet passing through the solar system. Because of these developments, the new pictures pushed the situation into a higher level of priority. The United Nations activated a planetary defense mission that had never before been directed at any object coming from beyond the solar system. Planetary defense exercises are usually reserved for testing how well agencies can detect, track, and model objects that might one day present a real danger. Using that framework for an interstellar object that is not expected to come near Earth immediately drew attention. It suggested that 3IATLAS was now seen as important enough to justify procedures normally used for impact risk training. The latest images showed why agencies felt they needed closer monitoring. 3IATLAS displayed a long, narrow tail and a second structure pointing toward the Sunday. This second structure is often called an anti-tail. In simple terms, an anti-tail appears when dust and particles arrange in a way that makes the line seem to point back toward the Sun instead of away from it. In many comets, tails look broad and somewhat diffuse, like a soft fan of material stretching out into space. In this case, both the tail and the anti-tail appeared sharply defined and stable. Over time, the lines held their shape instead of breaking into different branches or shifting direction. That stability is unusual because comet structures often respond quickly to changing sunlight, rotation, and streams of gas and dust leaving the nucleus. Their size and clarity suggested that a stronger or more organized force than simple warming ice might be involved. Typical comet activity is driven by ice turning directly into gas as the object approaches the Sun, a process known as sublimation. This process can create jets and streams, but they usually change shape as the comet turns and as the surface breaks down. With 3IATLAS, the structures remained intact over a very large distance. No official report claimed that the object was artificial or dangerous, but the odd combination of length, brightness, and stability gave scientists reason to pay much closer attention. The decision to start the defense exercise marked a clear shift. 3IATLAS was no longer treated as a distant visitor that could be sampled occasionally. It became part of a coordinated effort involving observatories and agencies across several countries. The International Asteroid Warning Network announced a full observation campaign running from late November 2025 to January 2026. That interval covers several weeks in which the object would be bright enough and close enough for many telescopes to track. Extended campaigns like this are usually assigned to objects that require very careful monitoring, either because they come near Earth or because their orbits remain uncertain. This makes the choice of 3IATLAS stand out, because it does not come anywhere near the ranges usually associated with real danger. The network itself has a short but important history. Since 2017, it has organized 8 official exercises, and each of those focused on asteroids that passed relatively close to Earth or had a small but non-zero chance of impact. In those earlier cases, the goal was to test how well the community could follow a potentially risky object and share updated predictions. Selecting an interstellar visitor for the first time meant they were applying the same level of organizational weight to something that should, in theory, be harmless. The network released an explanation for the campaign, stating that comets create special difficulties during measurements. A comet is not just a solid rock, it is surrounded by a glowing halo of gas and dust called a coma. That coma can expand and shift, and when it does, it can make the central nucleus appear in a slightly different position on images. If astronomers do not track this behavior carefully, the calculated orbit can drift from reality. In that sense, a continuous flow of data is important, and a multi-week campaign helps reduce the uncertainty. This reasoning sounded technically sound and responsible, yet it still did not fully explain why a full-scale planetary defense exercise was required instead of a more routine observation program. The official statements described the campaign as a valuable chance to practice using real data from a fast-moving visitor. Training is a necessary part of planetary defense, and agencies have often said they need to test their systems on real objects. Even so, many observers noticed that the tone used by the agencies was especially cautious. The wording seemed to lean toward calming the public rather than simply sharing enthusiasm for an unusual scientific opportunity. When the Minor Planet Center released its report, several lines encouraged astronomers to use as many telescopes as possible to watch every change in brightness, structure, and direction. That level of urgency is not commonly seen for a comet that poses no threat. NASA repeated that Atlas is not a danger to Earth, but its public comments focused more on reassurance than on detailed explanations. The agency did not walk through the complete reasoning behind the risk assessment. The European Space Agency emphasized that this exercise would strengthen cooperation between observatories and improve global readiness. That explanation sounded more diplomatic than scientific, as if the main message was about unity and preparedness rather than about the object itself. These careful and somewhat restrained statements created a sense that something about 3IATLAS remained unexplained in official channels. Another reason the decision stood out was the limited number of previous exercises. From 2017 onward, only a handful of objects have been considered serious enough to justify a formal defense drill, and all of them passed close enough to Earth that small errors in the orbit made a real difference. 3IATLAS does not fall into that group because its closest distance is far beyond any realistic impact scenario. Despite that, the network moved as if they were preparing for a live test. The structure of the campaign and the repeated requests for continuous data resembled exercises designed for potential hazards. This suggested that they wanted to understand the object in as much detail as possible, even though they continued to say that the public should remain calm. Several astronomers pointed out a simpler reason for the extra attention. Interstellar objects travel quickly through the solar system, and their trajectories are influenced by both the sun and their own internal activity. A fast path leaves less time to gather data, so any chance to look at such an object must be used efficiently. This factor alone could justify longer and more intensive monitoring, and it is consistent with the public explanations. At the same time, the timing of the decision still felt unusual to many experts who follow these projects closely. If the reason was purely training, they wondered why a campaign had not been scheduled earlier using some other object. The most interesting part of the announcement for many independent researchers was not what the agencies said, but what they left out. The statements did not directly address the strange behavior that private observers had been discussing for months. They did not mention the repeating patterns in the tail, the way the anti-tail seemed to hold a straight, narrow form, or the reports of brightness changes that did not match simple models of gas release. Instead of confronting these points, the agency spoke in general terms about data quality, coordination, and practice. This reluctance to acknowledge the unusual features led some astronomers to suggest that the campaign might be doing more than advertised. It might gather the highest possible resolution data while avoiding language that could cause public concern or speculation. Interstellar objects cannot be predicted in the same way as long-known asteroids because they come from outside the established catalogue of orbits. For many of them, there is no previous past to compare with and no long-term record of behavior. That means the object could begin to act in ways that challenge standard theories without much warning. Agencies may be concerned that 3IATLAS could show strong non-gravitational forces, rapid changes in outgassing, or other unusual dynamics as it moves through the inner solar system. From that perspective, a broad and quiet observing campaign makes sense. It allows them to build a dense set of measurements without making strong public claims in advance. As the exercise began, the key question for many scientists and interested observers was why the activation occurred at this specific moment. If nothing about 3IATLAS were unusual, it would be difficult to justify such a large commitment of telescopes, time, and coordination for something that should be harmless. The contrast between the calm tone of the official statements and the scale of the campaign made people look more closely at the images released by independent astronomers. These images soon became central to the discussion. The new images taken by independent astronomers revealed details that were not described in agency press releases, and this gap changed the tone of the wider investigation. The most widely discussed picture came from Mitsunori Samura, who used a half-meter telescope to capture a long, narrow tail, stretching nearly 5 million kilometers, and an anti-tail rising toward the Sunday. The length alone would have been impressive for any comet. However, the clarity and stability of the structure made it stand out even more. The tail did not show the broad, sweeping shape that many comets display. Instead, it formed a thin, defined line that appeared to hold its shape over an enormous distance without breaking apart. Samura's image was soon compared with photographs taken by Peter Carson and another observer, named Walter. Even though they used different telescopes and captured their images at different times, the results were consistent. Each photograph showed the same narrow tail, the same clear anti-tail pointing toward the sun, and the same stable structure stretching across a large distance. All three sets of observations displayed the same pattern. The images shared by independent astronomers drew wide attention because they appeared clearer than the ones released by NASA. Many viewers wondered why people using half-meter telescopes could produce pictures with sharper detail than agencies operating large observatories and space-based instruments. NASA explained that their systems collect data using longer exposure times to support measurements that require precise calibration. They also noted that the raw files often look dim until they are processed. Even so, the public noticed that the independent images were consistent across several observers and showed structural features that were difficult to overlook. This consistency made people question whether the differences came from equipment, timing, or choices about what the agencies decided to release. One of the most striking features was the anti-tail. In the new images, it appeared as a bright, narrow column more than 1 million kilometers in length. The column pointed directly toward the sun, which is unusual because dust exposed to sunlight normally bends away from solar radiation pressure. The straight shape did not match what comet models predict. Instead of widening or curving, the anti-tail held a firm line, as if shaped by a force that kept the particles aligned over a great distance. When several observers captured the same feature with similar clarity, it strengthened the idea that this was not an artifact caused by image processing, sensor limits, or atmospheric distortion. It pointed to a pattern inside 3IATLAS that allowed the jets to form a stable geometry. The stability of these jets raised questions about whether the object was responding to sunlight in a simple way. A natural comet changes continuously as ice turns to gas. That gas escapes outward and carries dust with it, creating shapes that shift as the nucleus rotates. If the outgassing is strong, the trails often appear messy, with irregular branches and faint arcs that fade or brighten as the comet moves through space. The images of Atlas, however, showed lines that remained narrow, clean, and sharply defined. They did not show the usual signs of random shedding or uneven heating. To many observers, this gave the jets a structured appearance. Some viewers went further and suggested that the flow looked controlled, as if guided by a repeatable mechanism. That idea remains speculation, but the contrast between Atlas and common comets made the comparison difficult to dismiss. Another point that attracted scientific interest was the brightness of the coma. In typical comets, the coma shows uneven patches where different surface areas heat up and release gas at different rates. These patches can create lumpy shapes or faint shadows depending on the angle of the sunday. But Atlas displayed a smooth, uniform glow even as it moved rapidly through space. This raised the possibility that the material coming off the object might come from deeper layers or from a process that spreads the release more evenly across the surface. A uniform coma does not prove anything unusual, but it does suggest that the activity is organized in a consistent way rather than being driven by scattered pockets of ice near the outer crust. This detail prompted questions about what might be happening inside the object. Even astronomers who believed the object was natural acknowledged that the features seen in the images were highly unusual. The structures behaved more like organized streams than like random dust clouds. Organized streams require steady conditions, but comets typically experience fluctuating temperatures and rapid changes as they travel. The smoothness and stability of Atlas stood out against that background. As the pictures spread online, the debate intensified. Many people compared the independence and clarity of these results to the cautious tone used by agencies in their public statements. It became clear that the gap between official descriptions and independent observations played a major role in fueling public interest. People wondered why the agencies downplayed details that were visible in images produced by multiple observers. The spread of these images added weight to questions that had already surfaced about the nature of 3IATLAS. Viewers were especially focused on how precise the structures appeared. They pointed out that the next round of measurements might reveal whether the object maintains this consistency or whether it begins to shift as it approaches different regions of sunlight. That uncertainty created anticipation for the next phase of the investigation. The appearance of the 12th anomaly, identified by Professor Avi Loeb, became one of the most discussed clues because it centered on the rotation of 3IATLAS and the behavior of its long jets. The idea behind this anomaly is simple to understand but difficult to explain in a scientific model. If the object rotates every 16 hours, as earlier measurements suggested, then the jets should show signs of motion. A rotating body throws off material in a pattern that naturally curves as the object turns. Over a short distance, this might be hard to see, but over more than 1 million kilometers, the curve becomes noticeable. Instead of forming straight lines, the jets would stretch and twist into spirals. This effect has been documented in many comets. When the rotation is clear, the trail shows gentle arcs or repeating curves that follow the object's spin. The new images of Atlas, however, did not show these expected curves. They displayed straight streams with sharp edges, and this difference was difficult to ignore. Researchers expected at least some distortion because sunlight heats different parts of the surface at different times. Uneven heating usually creates uneven flows, and those flows produce minor bends or waves in the dust. The fact that the jets remain straight suggested that the rotation speed might not match earlier readings. Loeb proposed that Atlas may have slowed down since the summer. This idea was noteworthy because slowing down is not typical for comets. When a comet releases material, the force can speed up its rotation rather than slow it. A sudden decrease in rotation would require an external force acting against the spin, and no simple natural process explains this behavior clearly. The behavior of Atlas seemed out of order when compared to patterns observed in other objects. The stable geometry of the jets, the uniform glow of the coma, and the narrow lines that extended over great distances all contributed to the puzzle. Another possibility raised by Loeb is that the jets may not be constant. Instead, they might fire in short bursts that occur only at specific times. If deep valleys on the surface hold ice that remains in shadow for most of the rotation, sunlight may reach them only at certain angles. When that happens, a brief pulse of energy could produce a focused jet that extends outward in a straight path. This idea could explain why the jets did not appear twisted. It suggests that the jet, once launched, travels a long distance without being reshaped by further rotation. This scenario provides a potential natural explanation, but it also leads to new questions about the structure of the object. If the surface contains deep valleys that restrict light, then the interior might have a complex shape that channels material in specific directions. That kind of structure is not impossible in natural bodies. but it would require a history of formation that differs from common comets. Many comets break apart, resurface, or fracture over time. A stable pattern of deep valleys suggests a more organized internal arrangement that has been preserved over a long period. Loeb emphasized that more data is needed before reaching any conclusion. The appearance of the jets could still be influenced by factors not yet measured. For example, changes in the nucleus, unusual thermal properties, or variations in density could all affect how material escapes. But even with these possibilities, the question remains open because no single explanation fully accounts for all observed features. The rotational behavior of ATLAS, combined with the long straight jets, forms a case that cannot easily be matched with current comet models. The search for a clear explanation continued as more astronomers reviewed the available data. Some argued that natural processes could still account for the behavior if the nucleus had an unusual shape, or if the dust particles were larger or heavier than typical comet grains. Larger particles would resist bending from sunlight and solar wind, allowing them to form straighter lines. Others pointed out that this possibility would need confirmation through spectroscopic measurements that track particle size distribution. Until such measurements are completed, it remains one possible scenario among several. Observers noted that the stability of the jets over long distances implies that the internal conditions of ATLAS remain consistent as it moves through space. This consistency contrasts with comets that show strong changes when heating increases or when they enter regions influenced by solar wind streams. The fact that ATLAS did not show these shifts in the recent images suggests that something about its composition or internal pressure system operates differently. As the discussion grew, the scientific community remained careful. Researchers emphasized that unusual observations do not immediately point to non-natural explanations. Many reminded the public that several interstellar visitors have shown unexpected traits. Without a long history of previous encounters, it is difficult to create a firm baseline for comparison. ATLAS may follow rules that are simply uncommon among the objects observed so far. Even so, the 12th anomaly continued to draw attention because it touched on a fundamental measurement: rotation. If the rotation is not behaving as expected, then the forces shaping the jets must also differ from standard models. Loeb's suggestion about bursts from deep valleys offered a way to reconcile straight jets with a rotating body. It provided a mechanism that fits within natural physics, yet it also highlighted how little is known about the internal structure of 3IATLAS. If the surface of 3IATLAS has features that allow such steady and focused flows, then the object may be more solid or more organized than the fragile bodies that are normally found in interstellar space. Many comets that travel through the solar system are made of loosely packed ice and dust. They break apart easily, shed material in uneven ways, and rarely show stable channels that guide gas into long, straight streams. A comet made from soft material would not typically support a consistent release pattern over many days. It would crumble, rotate unevenly, or display a trail that spreads out into a wide, cloud-like shape. That is why the behavior of ATLAS caught immediate attention. The situation becomes even more unusual when the length of the jets is considered. A jet that stretches over 1 million kilometers must leave the surface with significant speed. When gas and dust escape at high speed, they reveal changes in rotation and changes in how the surface heats. Even small variations in motion should bend the stream. If the object rotates slowly, the flow should shift gently. If the rotation is faster, the curve should be stronger. Either way, the line should not remain completely straight. Yet the images show almost perfect lines that do not show bending or twisting. They appear more like narrow beams than like natural trails. This appearance led some viewers to compare the jets to controlled exhaust rather than to the soft release of gas seen in normal comets. The idea is speculative, and no evidence currently supports an engineered explanation. However, the visual similarity between these long, stable patterns and the organized streams produced by controlled systems made people search for deeper answers. Even observers who reject artificial explanations agreed that the geometry challenges standard models. When natural material escapes at high speed from a rotating object, it does not normally settle into crisp lines. As astronomers continue to study the anomaly, the larger question becomes more important because the rotation of Atlas influences every part of its behavior. The rate of rotation affects how sunlight warms the surface, how jets rise from shadowed areas, and how dust spreads once it leaves the nucleus. If Atlas is not spinning in the way scientists expect, then the rest of its activity may not follow predictable patterns. A mismatch between expected rotation and observed jets could indicate that the object is operating under conditions that differ from known natural models. This issue becomes even more critical when examining the next strange feature, which appears in the way the anti-tail moves through the solar wind. The solar wind is a fast stream of charged particles that flows outward from the sun at about 400 kilometers per second. It pushes dust and gas away from any comet, shaping tails into curved forms that bend outward. The force is strong enough that even dense material rarely moves against it for long. Yet the anti-tail of 3IATLAS pushed directly through the solar wind, and this behavior surprised many astronomers. A structure that remains stable while facing the solar wind must carry a large amount of mass, or it must leave the surface at speeds that overcome the incoming flow. The strength and firmness of the anti-tail cannot be explained by weak outgassing. This led Professor Avi Loeb to calculate how much material the object might be losing. His estimates suggest that several billion tons of matter have escaped from the surface in the last 2 months. That value is extraordinary, even for a comet under heavy solar heating. While comets commonly lose material as ice turns into gas, the rate depends on the surface area exposed to sunlight. In this case, measurements from the Hubble Space Telescope show that Atlas has a nucleus far too small to produce the necessary amount of gas through normal sublimation. If the surface area is limited, the object cannot release that much material at the rate observed. Under ordinary conditions, the anti-tail should be weaker, more diffuse, or partially broken. Instead, the column remains clear and strong over distances reaching 1 million kilometers. This contrast between expected behavior and what is actually seen has led researchers to reconsider what kind of process might be active inside the object. Loeb noted that a technological thruster could produce the same level of acceleration with far less mass loss because a controlled exhaust moves much faster than gas created by sublimation. This concept is hypothetical and cannot be accepted without evidence. Still, the comparison highlights the difficulty of explaining the anti-tail using only natural processes. If sunlight and simple gas release cannot shape the observed pattern, then scientists must consider whether additional conditions exist inside Atlas. Since the solar wind is continuous, Any natural plume of dust should bend or scatter as it interacts with the incoming particles. The fact that ATLAS continues to produce a column that moves in the opposite direction raises a serious question about the forces acting on the material. One possible explanation is that the particles leaving the surface are denser or heavier than expected. Heavier particles experience less push from the solar wind and can maintain a straighter path. However, this explanation brings its own complications. Spectroscopic data collected so far does not show strong signs of unusually heavy elements. Without clear evidence of such particles, the theory remains incomplete. Another possibility is that the internal temperature of ATLAS is higher than predicted. If deeper layers are warmer, they could release strong flows of gas and dust that maintain their shape longer. However, astronomers have not detected thermal readings that confirm this idea. The temperature measurements gathered do not suggest unusually hot regions. Without thermal evidence, the role of internal heat remains uncertain. As each potential explanation is considered, new questions appear. If the material is heavier than normal, why does the spectroscopic data not show it? If the interior is warm, why do the infrared measurements not reflect this? If rotation is slow, what caused it to change? If rotation is fast, why are the jets not curved? Every attempt to match one feature to a natural model reveals another missing piece. The situation grows more complex as new images show the same stable geometry with increasing clarity. The next major step for researchers is to gather detailed spectroscopic measurements, which can reveal the chemical makeup of the material. Spectroscopy can identify the types of molecules and particles in the antitail. If the data shows that the gas behaves like ordinary comet dust, the puzzle will deepen because natural dust should not hold its shape against the solar wind in this way. If the data reveals unusual materials, that will open a new set of questions about how such material formed and how it behaves under solar heating. These spectroscopic readings are essential because imaging alone cannot answer the deeper questions. Images show structure, shape, brightness, and direction, but they do not show composition. Composition determines how dust responds to sunlight, how fast it spreads, and how stable it remains over distance. A narrow stream requires particles with specific properties. A long-lasting antitail requires material that either resists solar wind or moves with remarkable speed. Without understanding what the material is made of, the behavior cannot be matched to a known model. If upcoming spectroscopic measurements confirm that ATLAS is shedding normal comet material, then the search for an explanation will become more challenging. It would mean that everyday dust and gas, under ordinary physical laws, are somehow producing structures that break expected patterns. Such a result would point back to the possibility that ATLAS has internal conditions that have not yet been measured. It could involve unusual density, unusual pressure, or structural features deep inside the object. It may even mean that some part of the object's behavior is influenced by processes that have not been fully explored in interstellar bodies. For now, astronomers continue to gather data while maintaining a careful, neutral stance. They emphasize that the observations are real, the structures are unusual, and the explanations remain uncertain. They also note that interstellar objects have surprised the scientific community before. With limited examples to study, every visitor adds new information. ATLAS may belong to a category of objects that rarely enter the solar system, and its behavior may follow rules that differ from familiar comets. As more images and measurements arrive, the scientific discussion is expected to grow deeper. The focus will shift toward comparing all available data, rotation estimates, mass loss calculations, jet geometry, and particle composition. Together, these elements will help determine whether the observed patterns can be explained by natural processes or whether the object represents something not yet defined. For now, the researchers continue their work, preparing for the next round of observations and the next set of results. This brings us to the next important event in the story. As 3IATLAS continues its path toward Jupiter, researchers are preparing for an encounter that may reveal clues that cannot be seen from Earth. The region around Jupiter is shaped by one of the strongest gravitational fields in the solar system. This influence extends outward through a large zone known as the Hill radius. Inside this boundary, Jupiter's gravity becomes dominant over the pull of the Sun for small objects. Anything that enters this region can remain bound to Jupiter, at least temporarily. It may drift in orbit, instead of continuing along its earlier path. Because Atlas is expected to cross directly into this boundary on March 16, 2026, many astronomers consider the event one of the most important opportunities to study the object under new conditions. The exact timing and location of the crossing led some researchers to wonder whether the encounter is simply a coincidence of orbital mechanics or whether it may expose patterns that have not been visible so far. Professor Avi Loeb pointed out that the distance at which Atlas will cross the Hill radius adds even more significance. If the object releases material or fragments while inside this zone, the pieces could remain in orbit around Jupiter instead of dispersing back into deep space. A fragment that stays inside this gravitational region would be easier to observe over longer periods. This raised questions about whether the object might consist of smaller components or layers that could respond differently once separated from the core. Since Jupiter acts as a natural trap for passing bodies, the encounter offers a rare chance to detect behavior that cannot be studied under normal conditions. NASA plans to use the Juno spacecraft to listen for radio signals during the encounter. Juno will scan frequencies from 50 Hz to 40 MHz, which may reveal electrical patterns or interactions generated near the object. Natural dust and gas can sometimes produce faint radio signatures when charged particles move through magnetic fields. At the same time, more organized radio patterns might indicate processes that deserve further study. The presence of any signal would not confirm anything unusual by itself, but it would provide researchers with new data that could be compared to models of comet activity. The European Space Agency has also taken interest in the event. Its JUICE mission has already captured early observations of Atlas during its approach. Although the data will not arrive until early 2026, due to slow transmission speeds, this delay is expected because spacecraft far from Earth cannot send large volumes of data quickly. Even with this explanation, the timing has fueled curiosity, especially for people who have followed Atlas closely. By the time the information arrives, the encounter will already have passed, making the data less useful for real-time adjustments. Still, the delayed results may help scientists check their models and compare behavior before, during, and after the Jupiter crossing. Some astronomers believe the encounter may show whether Atlas responds to changes in gravitational pressure. When a body moves into a region controlled by Jupiter's gravity, the forces acting on it shift in subtle ways. These shifts may affect jets, fragment release, rotation rate, or brightness. If the object changes its direction or intensity while inside the Hill radius, observatories on Earth may be able to detect the shift. Even minor variations could provide clues about the object's interior structure or how its material interacts with external forces. Because ATLAS has shown unusual behavior in earlier observations, each possible outcome adds new layers to the investigation. Many researchers consider this encounter one of the defining moments of the entire study. As ATLAS approaches Jupiter, a larger question grows more urgent. If the object continues to behave in ways that do not match natural models, then what will the next gaps in the data reveal about the information that has not yet been shared with the public? The lack of consistent updates from major space agencies has become one of the most unsettling parts of the ATLAS story. Each missing detail or delayed message leads to more questions than answers. NASA and the European Space Agency have released only a limited number of updates, and their statements often focus on reassurance rather than on providing new data. Many people expected high-resolution images or precise measurements. Instead, only a small collection of observations has been published. This gap in information becomes more noticeable when independent astronomers continue to share detailed pictures that display structures the agencies have not discussed. The difference in transparency has caused some viewers to wonder whether the agencies are being cautious, selective, or unsure about how to interpret the data. The careful tone used in public statements has added to this perception. While agencies often avoid speculation in early stages, the limited flow of information has made the situation more difficult for both researchers and the public. The JUICE mission added another layer to the uncertainty because, although it has already collected data, none of the information has yet reached Earth. The delay has a technical explanation, but it still shapes public perception because the timing seems unusual. By the time the data arrives, the encounter will be nearly complete. Without early readings, scientists cannot compare the behavior of ATLAS during the approach with the behavior inside the Hill radius in real time. This prevents researchers from correcting earlier measurements or updating models quickly. The delay does not indicate anything hidden, but it does shape the way the public interprets the event. Some researchers have compared the current situation to earlier moments in the history of space exploration. They point to the long period of quiet following the detection of unusual signals by Voyager, or the long silence surrounding the early analysis of the object called Oumuamua. In those cases, slow or incomplete data release created long intervals of uncertainty. A similar pattern now seems to be forming with ATLAS. The limited communication from agencies does not necessarily indicate a problem, but it increases the difficulty of forming clear, up-to-date interpretations. The missing details also affect how scientists study the object's behavior. Without consistent measurements, it becomes harder to confirm changes in brightness, rotation, or tail structure. Observers have noted that ATLAS appears to shift between updates in ways that are hard to confirm. Sometimes the jets appear brighter, sometimes the coma shows a different shape, and sometimes the anti-tail looks more defined. But without official data to support or reject these impressions, many predictions become difficult to verify. A gap in data makes it challenging to tell whether the changes are part of a natural pattern or whether they indicate something unusual. When observations come from different instruments with different levels of detail, inconsistencies can arise without clear explanations. This uncertainty makes the Jupiter encounter even more important. A strong external force, such as Jupiter's gravity, can create changes that are easier to detect. If ATLAS reacts to the new environment, scientists may finally have evidence that distinguishes between natural and unusual behavior. But until the data arrives, and until the agencies provide a complete picture, observers are left with partial information. Without official data, it becomes difficult to confirm whether these changes are natural or unusual. Some astronomers believe that major space agencies may be waiting for stronger evidence before making decisive public statements. They argue that when an object displays unusual behavior, researchers often need extra time to verify measurements, rule out instrument errors, and examine whether the patterns are consistent over many sessions. Scientific caution is normal, especially when the data comes from different types of sensors and from telescopes operating under different conditions. Yet other observers take a different view. They believe that the quiet approach only increases suspicion, especially because 3IATLAS moves quickly and continues to produce features rarely seen in other comets. When updates remain infrequent and official comments remain vague, the investigation feels incomplete. Each gap in information leaves more room for speculation, and the public is pushed to rely heavily on independent observations. As more people turn to amateur astronomers for frequent updates, the contrast between official silence and detailed private reports becomes sharper. The missing pieces give the story an unsettling tone because they suggest that major agencies may be preparing for findings that challenge standard explanations. Some researchers have commented that these situations are not unusual in astronomy. Data sometimes arrives more slowly than expected, and analysts often choose to avoid early conclusions. Still, the lack of clear information remains noticeable. As more viewers ask why key data is missing, the mystery surrounding ATLAS deepens. If the silence continues, many wonder what the next phase of observations may reveal that has not yet been shared with the public. The closest approach of 3IATLAS on December 19, 2025 is considered one of the most important milestones in the investigation. At a distance of around 270 million kilometers, the object will still be far from Earth. However, this geometry will allow telescopes to collect clearer and more stable measurements than at any other point in its path. Many observatories have prepared schedules that prioritize ATLAS during this window because small differences in angle and brightness can be measured more accurately. Researchers hope that this moment will provide the best opportunity to study the object's behavior before it moves deeper into the outer regions of the solar system, where sunlight becomes weaker and detailed measurements become more difficult. Scientists plan to examine ATLAS using spectroscopy, temperature readings, and high-resolution imaging of its tail structure. Spectroscopy is especially important because it reveals the chemical fingerprint of the gas and dust leaving the surface. Each element and molecule absorbs and emits light in specific patterns, making it possible to identify what kind of material is present. If ATLAS behaves like a natural comet, the readings should show typical signatures from water vapor, carbon compounds, and other elements commonly found in icy bodies. But if the readings show unusual elements or unexpected ratios, the interpretation may shift. Scientists may need to consider whether the object formed in an environment different from that of normal comets, or whether it has undergone processes not seen in other interstellar visitors. Astronomers also hope to measure heat coming from the nucleus. A natural comet warms only through sunlight, and its internal temperature should match what models predict for an icy body exposed to the sun at this distance. If ATLAS shows additional heat, the readings may indicate that internal activity is stronger than expected. Small increases in temperature could point to deep layers releasing gas, or to internal structures that trap and redistribute heat. In either case, such results would require researchers to rethink how interstellar comets evolve over time. While these tests sound straightforward, scientists caution that predicting the outcome is difficult because ATLAS has already broken several expectations. The brightness of the tail is another key measurement because the glow reveals how much material is leaving the surface. This flow affects both the direction and the speed of the object. When a comet releases more gas, it may slow down, speed up, or shift slightly, depending on where the material escapes. A natural comet often shows scattered patterns as its jets respond to changes in sunlight. ATLAS, however, has displayed narrow and stable lines for months. This makes the upcoming measurements more important because any deviation from this pattern may show how the object responds to stronger solar radiation near its closest approach. Ground-based observatories around the world are preparing to track these fine changes in brightness and structure. Small adjustments in the shape of the tail may reveal new information about the internal layout of the nucleus. If deeper layers begin releasing more gas, the pattern of the tail may widen or show small irregular features. If the jets remain narrow and steady even under greater heating, this could support the idea that ATLAS has an unusually stable structure, or that the flow of material is guided in a way not seen in normal comets. Each detail will help scientists determine whether the object fits into existing models or whether it continues to challenge the standard understanding of interstellar bodies. For many researchers, the closest approach serves as a final major test before ATLAS moves farther from the Sunday. Once the object begins traveling into darker regions of the solar system, its brightness will decrease, and collecting high-quality data will become more difficult. Instruments that rely on reflected sunlight will lose sensitivity, and many types of measurements will no longer be possible. Because of this, the urgency to gather reliable information now is stronger than ever. This moment may determine whether the object behaves like familiar comets or whether it retains properties that do not match natural models. Viewers following the investigation understand that this moment may define the next phase of the story. If ATLAS continues to defy expectations, the pressure to explain its behavior will increase. Scientists will need to reconcile the measurements taken during closest approach with the unusual features recorded over previous months. These include the 5 million kilometer tail, the rotation puzzle, the strength and stability of the anti-tail, and the large mass loss that cannot be fully explained by ordinary sublimation. Combined with the limited information released by major agencies, each of these factors contributes to the sense that the object does not fit comfortably within standard comet categories. As December 19th approaches, one question remains at the center of the investigation. If ATLAS is not behaving like a normal comet, then what will the upcoming measurements reveal about its true identity? The story of 3IATLAS now leads to its largest question. Every anomaly, every delayed update, and every unexpected measurement suggests that something far more complex may be unfolding. The long tail, the unusual stability of the jets, the behavior of the anti-tail against the solar wind, and the quiet tone from major agencies all point to an object that continues to resist simple explanations. With each new observation, the picture becomes more complicated rather than clearer. Scientists acknowledge that the possibility remains that all observations will eventually fit within natural boundaries. Objects from other star systems may carry different compositions or structures that have not been studied before. The behavior of ATLAS could reflect conditions common in regions beyond the solar system that Earth has not yet explored. But until more data arrives, each new anomaly adds weight to the idea that the object's behavior may require new models or a deeper understanding of interstellar material. As the investigation reaches this critical stage, researchers continue preparing their instruments, refining their predictions, and studying each new image released by independent observers. The coming months may bring clarity or deepen uncertainty. Either way, the measurements taken during closest approach will play a central role in shaping the final interpretation. For now, the scientific community waits for data that may redefine what interstellar objects can be and how they behave. The next phase of the Atlas story depends on what the upcoming observations reveal.